In 2-2, we are going to learn to determine the truth value of a negation, a conjunction, and disjunction. Then, we will learn how to represent them using truth tables and Venn diagrams. First, let's go over some vocab. A statement is a sentence that is either true or false. The truth value of a statement is either T for true or F for false. We can also use letters like P and Q to represent a statement. For example, the sun is hot. This statement is true, so its truth value would be T. A triangle has 3 sides. This statement is true, so its truth value would also be T. The negation of a statement is the opposite of the statement. It also has the opposite truth value. For example, take our previous statement. A triangle has 3 sides. The negation of this statement would be not P. A triangle does not have 3 sides. We would represent negation using not P. When you join multiple statements with the word and or the word or, it is called a compound statement. A compound statement that specifically uses the word and is called a conjecture. A conjecture can only be true when both of the statements are true. For example, P. There are 60 minutes in an hour. The truth value is T. Q. There are 7 days in a week. The truth value is T. Because P and Q are both true, then the conjecture P and Q is true. The other type of compound statement uses the word or instead of and. This is called a disjunction. For example, P. Doug the dog has a red toy. Q. Doug the dog has a blue toy. P or Q. Doug the dog has a red toy or Doug the dog has a blue toy. For a disjunction to be true, it only needs one of its statements to be true. So, if Doug has either a red toy or a blue toy, the disjunction is true. If Doug has neither, then it is false. Now that we've learned some vocabulary, let's try and make a truth table. A truth table is a way to organize the truth values of statements. Let's construct a truth table for not P or Q. We need to make columns with headings that contain each of the original statements, the negations of the statements, and the compound statement. Then, we list all the possible combinations of truth values. We use these truth values to figure out the truth value of the negation, and then use the truth values to determine the truth value of the compound statement. We can also use Venn diagrams to illustrate a conjunction. For example, P and Q. A rectangle is a quadrilateral, and a rectangle is convex. Look at the Venn diagram. We see that the rectangle, R, is found in the intersection of the set of quadrilaterals and the set of convex polygons. A disjunction can also be shown using a Venn diagram. P. A figure is a quadrilateral. Q. A figure is convex. P or Q. A figure is a quadrilateral or convex. In the diagram, the disjunction is represented in the union of the two sets. This includes all polygons that are quadrilaterals, convex, or both. We chose this as our most important topic because it encompasses a lot of new vocabulary and can be hard to grasp. In a couple of minutes, we will be explaining how to make a proof. Before we do that, let's learn some of the properties that make up a proof. The reflexive property states that a value is equal to itself. So, AB equals AB. The symmetric property says that if one value is equal to another value, then the second value is equal to the first value. So, if AB equals CD, then CD equals AB. The transitive property says that if a first value is equal to a second value, and a second value is equal to a third value, then the first and third values are equal. So, if AB equals CD and CD equals EF, then AB equals EF. Then there are the commutative and associative properties. The commutative property of addition says that A plus B equals B plus A. The commutative property of multiplication says that A times B equals B times A. The associative property of addition says that the quantity of A plus B plus C is equal to A plus the quantity of B plus C. The associative property of multiplication says that the quantity of A times B times C is equal to the quantity of A times the quantity of B times C. We chose this as our free choice because it is an important part of making proofs and is also fairly easy to understand.
So I got a simple example proof from the geometry book in lesson 2.7. This problem is number 2 on page 147. Let's write the given, prove, and draw out the picture. Okay, so Wx is congruent to Yz. Prove Wy is equal to Xz. First, as always, in our statements is that we write out our given. The reason is given. Next, we can say that Wx plus Xy equals Wy, and also Yz plus Xy equals Xz. The reason would be segment addition postulate. Here we can substitute Yz in the second equation with Wx because they equal each other. So, number 4 would be Wx plus Xy equals Wy, and Wx plus Xy equals Xz. You can see that both of the equations are on top of each other and are equal. So that means we can use substitution to say Wy is congruent to Xz. We think this is the hardest topic in Chapter 2 because it was introduced and none of us had really understood the mechanics of proofs until much later. It was all in all a hard concept to grasp. The main problem for me in proofs is to think about what to do next in order to help you prove something, like how we can use the given and come up with the next step.